All right, so our final section in chapter 9. We're going to talk about representing functions. So we spent the first part of the chapter talking about what a series, what a sequence is, what a series is, how we decide if an infinite series converges, which is usually what's interesting to us. We found out some interesting facts about infinite series. We talked about the conditionally convergent alternating series and how that some strange things happen there. And we talked a couple of times about some famous formulas for constants, and we're going to come back to those today. We also talked about Taylor series, finding Taylor polynomials, approximating functions with polynomials. And what I want to do today is tie the power series and the Taylor series together, and show why we talked about both, and then answer Chris's question as to how power series are useful. Why do we use them? So let me start with a theorem. And this is what we call a uniqueness theorem. So our theorem is, and it's really a pretty cool idea. So if f is a power series, representation of small f, centered at some c with a radius of convergence r, then f is the Taylor series for f centered at c. So what this theorem is telling us is that no matter how we find a power series, yesterday we found a power series by looking at the terms and figuring out a general formula for the nth term. Today we're going to talk about finding power series, and we've done a little bit with it using the idea of a geometric series. No matter how we find a power series to represent our function, this theorem tells us that what that power series is the Taylor series. So all the properties that we required of a Taylor series, that the function at c agrees, the first derivative agrees, the second derivative agrees, so on and so on, that's going to be true about this power series. So no matter how we find this power series, it's the Taylor series, and we can use we know that it has all the properties of the Taylor series. So that's the first really cool idea from this section, is we can find it any way we want, and we know we have the Taylor series. So this is the link between our power series and our Taylor series. Actually, they're the same thing. So we've found them different ways. A lot of times it's easier to find a power series representation of a function than it is to find a Taylor series, and we'll do an example of that in just a little bit. So let me talk about operations with power series, and then we will work on answering Chris's question. So some operations. We need these when we start actually doing things with power series. And these all just come straight from from our definition of power series. So if we have our function is some power series, and g of x is some other, represented by some other power series. If we want to find the function of some constant times x, this is just going to be the sum of a sub n, k to the n, x to the n. So we just basically we're substituting kx in for x into our power series. F of x to the n power is the sum of a sub n x to the n times n. So again, we're just substituting x to the n in for x into our series. And the last one is if we're adding functions, we can just add, and we'll put a plus or minus. We can just add our coefficients. And all of these may change the interval of convergence. So when we perform these operations, we have to then retest our convergence to determine our interval of convergence. So these are the operations that we're going to use when we start actually applying these power series. So let's talk about one way, we've worked with this a little bit, one way we can find an easy way to find a power series representation of a function than calculating the Taylor series. Any questions about our properties before we're going? Yes? Capital N is a constant, yes. So just some other exponent. Yes?
On the first one, the x to the x.
Sorry?
The x to the next one on the first one, so on the left.
Here?
No, on the left.
Oh, no, this is just k, f of k times x. So some constant, where k is just a constant. So we're taking the function, so say we have a power series for x, and we want to find the power series for 2x. So this, we would basically we're just we're substituting kx in for x into that expression. Does that make sense? Okay. All right, so the first easier way to find a power series is a geometric power series. And we've worked with this a little bit already. So if we want to find a power series representation of a function, we can use the properties of geometric series. So let's look at an example of that. So we want a power series for f of x equals 1 over 2 minus x. Now we could find the Taylor series, we could calculate our derivatives, calculate our coefficients for a Taylor series. When we have a fraction like this, calculating the derivatives can get kind of tedious. But let's look at this as a geometric series. If we look at this as the form, our function as the form a over 1 minus r. We want to put it in this form. So I'm going to divide everything here by 2. So our goal is to put this function in this form. So divide everything by 2. So I'm going to say f of x is 1/2 1 minus x over 2. And now this function is in the form of the sum of a geometric series. So here my r is 1/2 and a equals 1/2. So this function is going to be, I'm just going to write it as 1/2, the sum n equals 0 to infinity of x over 2 to the n.
You divided the whole.
I divided everything in the numerator and denominator by 2 to put it into this form. So this would be a power series representation for this function, and then we would go on and find our interval of convergence. We could do that. But what I wanted to show you here is the process for finding a power series based on a geometric series. Yeah.
And do we try and fit into that form because the function is just the sum, basically, of
Right.
the series?
Right. So our function is just the sum of that series. So if we can represent it as a geometric series, that's just an easy way to put our function in the form of a power series. If we can match it to our geometric series, because we know the sum. So if we think of this as the sum of a geometric series, we want to put it into that form so we can express it this way. Does that make sense? So if we're trying to find a power series, a geometric power series, this is the procedure. We want to put it in this form. Now I'm going to go through the next several examples. Are going to go more towards Chris's question of how we're going to apply this. So these are classic examples of working with power series. So I want to find a power series f of x equals 1 over x, and we want a power series centered at 1. So we want to represent this as a power series centered at x equals 1. So what we're looking for here, and this 1 over x, the reason we're working with 1 over x is that our goal for this particular function is we want to get some kind of representation for the natural log of x. And 1 over x and natural log of x are related. So we want the form a over 1 minus r, and we want the series in terms of x minus 1. So because we're centered at 1, our terms of our series are going to involve x minus 1. So I want to rewrite 1 over x in terms of some quantity of x minus 1. So let's write 1 over x equals 1 over, and how can I write x in terms of x minus 1 so that it fits into this form? 1 minus x minus 1. Does this make sense what we did here? I want to fit this function into this form. I'm centered at 1, so my terms of my power series are going to be powers of x minus 1. So I want my ratio, my radius, my ratio, to be in terms of x minus 1. Does that substitution make sense? Okay. So now we have...
Would you 1 over negative x then?
what's that?
Would you You get 1 over negative x?
Oh, we have a minus and a minus here.
Okay.
So I have two minus signs, so that gives me the plus.
Where's the 1? Okay.
And the ones just go away, right?
Yeah.
We have a plus 1 here and a minus, or
Oh.
this is a plus 1, and we have a minus positive 1, so the ones subtract and I get 0. So I just, if I simplify this, I just end up with 1 over x.
Alright.
Okay? So my a is 1, and my r is minus x minus 1. So I can write this. So I can write this as a geometric series, the sum of the geometric series. So 1 over x is the sum, n equals 0 to infinity, of minus x minus 1 to the n. And I'm just going to rewrite this in more standard notation. 0 to infinity of minus 1 to the n, x minus 1 to the n. And this would converge when the absolute value of x minus 1 is less than 1. And we can, I'm not going to run all the tests, but we can find our interval of convergence is 0 to 2. So if we ran all of our tests, we would find our interval is 0 to 2. So now we have a power series representation for 1 over x. Now here is how we end up using these power series. This one was pretty easy to find. We found this power series for 1 over x. Now let's find a power series for natural log of x. Centered at 1. So we want to find a power series for the natural log centered at 1. Well, how is our natural log related to what we just did?
Integral.
It's the integral. The natural log is the integral of 1 over x dx. So, and when we do our integral here, we need to explicitly account for the constant, because the constant can become important when we're doing this power series expansion. So I'm going to write this constant of integration out here to make sure that we account for it. So this is, the natural log is going to be c, my constant, plus the integral of the sum, n equals 0 to infinity, of minus 1 to the n, x minus 1 to the n dx. And when I take this integral, I get that my natural log is my constant plus the sum, n equals 0 to infinity. I'm just taking, the only thing that my integration is with respect to x, so it only affects this term. So I get x minus 1 to the n plus 1 over, I forgot my minus 1, and n plus 1s, and we get a minus 1 to the n here. That stays in there. So I just integrated with respect to x. And there's my power series for natural log of x. We need to account for this constant. When x equals 1, the natural log of 1 is 0, and I plug in 1 here and I get 0, so I get that my constant equals 0. So sometimes this constant will come out to be non-zero, and we have to keep account of that.
You want to plug in?
So yeah, whatever, plug in the number that's going to make this 0, or 1, or something, something that you can work with easily. But usually you can pick it so that this is 0 and you find your constant when it's 0. So now we have that the natural log of x, we have a power series for the natural log of x centered at 1, is this sum. And we found this by integrating a power series that we had found already. So this is how we find new power series. This is how we apply it. And I'll talk a little bit about how we're talking about functions that we're used to working with, but we can use this for functions that are more complicated. If we test the endpoints, we find that the interval of convergence is 0, 2 for this power series. And when we worked with our alternating conditionally convergent alternating series, and I wrote an expression for the natural log of 2. We can plug in x equals 2 here, and I get that the natural log of 2 is 1 minus 1/2 plus 1/3 minus 1/4 plus ... And this was the alternating series that we worked with when we rearranged the terms and got half of this result. So this is where that expression comes from, is this power series representation for the natural log of 2. Questions on how we did that? So let's do one more example, and this one's a little more complicated, but kind of shows the power of using this approach a little more strongly. Let's find a power series for the inverse tangent of x centered at 0. Anybody have an idea how we might approach this?
Find 1 over 1 plus x squared.
What? Say it again.
Find the series from 1 over 1 plus x squared.
Okay, so Cole says we're going to work with 1 over 1 plus x squared. Why 1 over 1 plus x squared?
That's the derivative.
Okay, perfect. Very nice. So we know that the derivative of the inverse tangent is 1 over 1 plus x squared. This kind of looks like our sum of a geometric series, right? So let's look at g of x equals 1 over 1 plus x. Because we talked about operations with power series earlier. So if we find this, the representation for the power series for this, then we just substitute x squared for x, and we're set. So this is even closer to a geometric series. This is 1 over 1 minus negative x. So I can write this as the sum of a geometric series. So 1 over 1 plus x equals the sum, n equals 0 to infinity, of minus 1, I'm just going to write minus 1 to the n, x to the n. And 1 over 1 plus x squared now is going to be the sum (0 to infinity) of minus 1 to the n, x to the 2n. Using those operations with power series. So there's my power series. And the inverse tangent of x is going to be the integral of this quantity. and we're going to explicitly account for a constant. So we take this, we perform this integration, and I get that the inverse tangent of x is the sum, n equals 0 to infinity, of minus 1 to the n, x to the 2n plus 1 over 2n plus 1, plus our constant. And we substitute when x equals, I'm going to substitute x equals 0 in here. When x equals 0, my constant is going to be what? Inverse tangent of 0 is 0. Yes? Tangent of an angle is the sine over the cosine of the angle. So our constant is 0. So now we have a power series representation for the inverse tangent centered at 0. Just the sum from 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Now let's look back at where we started. Think about trying to find the Taylor series for the inverse tangent of x by the procedure we used before. Taking the derivatives, so we'd have to take the derivative of the inverse tangent of x, take the second derivative, take the third derivative, depending on how many terms we wanted, and then try to find a formula for the general term. That would be, like, I wish Griff were here, that would be messy, because he likes that word. That would be very messy. So we found a power series, and we integrated. So this is normally how we're going to apply power series. We're looking for something, we're trying to get a result. We look for a result that we have already. Can we differentiate it? Can we integrate it? And this leads us to for the inverse tangent, if we tested our intervals of convergence, we would say that we would find our interval for this particular series is minus 1 to 1, is when this converges. And this leads us to a very famous formula for pi over 4. The inverse tangent of 1 is 1 minus 1/3 plus 1/5 minus 1/7 plus dot dot dot, and that equals pi over 4. So pi over 4 is 1 minus 1/3 plus 1/5 minus 1/7, etc., etc. What's that?
Oh, it's just like a way to calculate the pi, okay?
Could be. Use some kind of algorithm like this. Now, to me, this is pretty amazing. We have this alternating series of rational numbers, ratios of integers, and the infinite sum is an irrational number. To me, that's kind of cool. So the nice thing about a power series representation is I talked the other day about finding integrals of non-elementary forms. So an example that I gave was if we had something like the integral of e to the x squared dx, we don't have a way to represent this integral, but we can write e to the x squared. We have a process now to write e to the x squared as a power series, and we can integrate that term by term, so we can come up with an expression for the integral of this thing, and if we're looking for a definite integral, we can find it to the whatever accuracy we want by taking as many terms as we want. So this is one way we would use power series, is to evaluate integrals that we couldn't evaluate otherwise. And I remember when I was in college, when we would do things, when we'd get to a problem, we'd get stuck. The first thing me and a group of friends would always say is, let's write a Taylor series. So we didn't know what to do, so we wrote our function as a Taylor series. Does that help us out? So that's really what happens with these kinds of things. Once you have this ability to work with these power series. So we were just talking about it. because we came to a problem and we were talking about finding the Taylor series for inverse tangent of x by taking all the derivatives, and I said that would be really messy. All right, so any questions about what we did here? So this, I hope this brings together what we've talked about this chapter. I really like the idea that the power series, if you find a power series, that is the Taylor series. We have all the properties of Taylor series. We determine our convergence by we have all these different tests that we talked about. And in series and convergence it really gets us really close to the heart of what calculus is all about. Calculus is all about limits and convergence and these infinite series, and it's really, to me, it's really fun to get, like, this is really one of the only times that we get that close. We get away from calculus as a tool using algorithms to calculate answers, and we get a little more closer to kind of the root of what calculus is really about.
So for e to the x squared, we just use the fact that we know the power series for e to the x, and then manipulate that?
Yes.
Because you can't like speed up.
Right, so e to the x is a series where it's relatively easy to find a Taylor series, because finding all those derivatives for e to the x is really easy. So a Taylor series for e to the x is easy to find.
And then you just plug in
Then
x
put
squared.
x squared for each term, and then you have that power series, and then you can integrate that term by term. Yeah.
So if you're evaluating this integral and you use series, you just leave the answer in the form of a series?
Mm-hmm.
Okay.
Yeah. And then sometimes, if you're lucky, with this one, it turns out that it's not represented, you can't represent this as what they call a closed form function. There's no representation for this. You can prove that there's no representation for it. But sometimes if you do this and you manipulate the power series, you get your answer and you say, oh, that's the power series for some other function. And then you realize what that is. So that does sometimes happen. Last thing I want to do is just list some common power series. Some of them I'm sure that you guys already recognize. We've already talked about 1 over 1 minus x, and that's a sum n equals 0 to infinity of x to the n. And for absolute value of x less than 1. We did 1 over 1 plus x. We worked with that one today. And that's a sum n equals 0 to infinity of minus 1 to the n x to the n. And this is for absolute value of x less than 1. This should be an x. E to the x, very, very common one. Sum n equals 0 to infinity of x to the n over n factorial. And this one's nice because it converges for all x. So this makes this series for e to the x is extremely useful. Sine of x, another very, very common one that gets used a lot. Sum from 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And this converges for all x, so that makes it extremely useful. And notice that for this one, we only have odd powers and factorials. We only end up with the odd powers and factorials. Cosine of x. And this one we get minus 1 to the n x to the 2n over 2n factorial. And that converges for all x, so another very useful one. And for this one we have the even powers and factorials. We did the natural log today. Let's see. For this, we did x minus 1. So I'm going to write the series for x plus 1. So this is minus 1 to the n minus 1, x to the n over n. And this is for minus 1 less than x less than or equal to 1. And we also did the inverse tangent. And that's for absolute value of x less than 1. So these power series get used a lot for various things. All right, any questions for today?
Are we not doing section 9 and 10?
We're not doing section 910. I don't, what is section 910? Yeah, so yeah, we're not going to do anything with 910. All right, there you go. Chapter 9 done.